I'm going to look into floating point precision errors because this lack of precision can affect our expectations when we're building up instructions in the node editor and when we're doing comparisons, etc. So floating point is a data structure that allows computers to perform calculations with real numbers in a binary format. So instead of base 10, like we are used to decimal, it's base 2. Now, just like base 10, there are some limitations in representing values. So for example, if I give you the fraction of 1/3, you know that this will have in decimal an infinite representation where you go like 0.333, etc. And you go on forever. Now, I cannot store an infinite representation in a computer. And so of course, let's say I give you a piece of paper and I tell you to write the decimal representation of the fraction, you're going to have to stop at some point. Now, this will make that these two values are of course not the same. This is a rounded up, truncated version of the fraction. And so similar thing will happen with floating point data. The thing is that it will happen with values that maybe you are not expecting it to happen. So for example, in binary, 0.1 has an infinite representation, just like this article here in exploringbinary.com goes into. This will make that, let's say that I get 0.1 converted into base 2 binary and then back into base 10 decimal. It will make that the value will have some garbage. So it will be something like 0.1000000 and then some leftover garbage from the truncation or the rounding up. And so when we have this happening, we're going to get values that are either a little bit to the right or a little bit to the left of the actual value that we think we are dealing with. So let's look into that in layout and just basically look at an example where we think we have a value, but it's actually something else. So here I have this constant scalar node where I type in 0.1. Then to that, I add 0.2, so it becomes 0.3. Then I multiply that by 10, and so it becomes 3. Now, I have here another constant node with a value of 3. And if I pass both of these through a logic node, and if I check if A is equal to B, I would expect the value of 1 to come out because, well, this is true. 3 is equal to 3. But what I get instead is the value 0 because the computer doesn't consider them to be the same. And so this can be problematic because I would expect something to come out of this and I get something else. One way to go about it is to use the compare nodes by true art. And so in this case, I have the compare scalar, but there are other ones. So for example, we have compare vector. That's very useful when we get into vectors as well. And so here, it's basically this node just performs one operation. It checks if source 1 is equal to source 2, outputs 0 if they are not, and outputs 1 if they are equal. And so in this case, just like in the logic node, we can see that it's telling me that they are not the same. The difference is that I have a tolerance port, and this tolerance will basically be a window, a little window that I can define that all the values that fall inside this window are going to be considered the same as the value that I'm checking against. And so this allows me to basically catch these errors and still have the comparison work as I expected. And so I can have a small window, or I can have a big window. So it depends on the magnitude of the values that we are working with, and if we are magnifying those floating point errors a lot. So in this case here, I have 3 and 3, and it goes through the compare node, and it still tells me they are not the same. But if I come here to this renamed constant scalar node to tolerance, and let's say I put the value of 0.001, now this tells me that these two values are the same. So this is a way to basically catch these issues. I also use a lot this epsilon node as a source of a small tolerance value. And you can find an article about machine epsilon in Wikipedia. And so I have, in this case, I have the float and the double. So really small values to use as a tolerance, as a window of comparison. Now, in this case, I just have the operation to check if one value is equal to the other. I don't have all these other operations. So here I just, for a demo purpose, I've built a compound where I have all those operations done based on this comparison. And so here I have the compare scalar with the tolerance going in, and then I have all the other operations inferred from this one. Now let's look into another example of where this sort of lack of precision can be quite problematic. So for example, here I have the function arccos. And so arccos has a range of values that is that it can process, and it can perform a defined value. So I can only input values that go from a -1 to 1 into arccos. If I give it something else to the right or something else to the left of that, I'm going to get an error. And so in this case, I have the value of 1.0001. And so if I pass that to arccos, I'm going to get not a number, it's undefined. Now, this is problematic because it's going to propagate onto all my other calculations. So here I have not a number, this multiply operation that uses that, also not a number, and so everything that uses this connection or it can be traced back into this this node will give me this error, and it will invalidate my node tree. So that's problematic. And so in this case, I know there is a specific range, and because these floating point errors, maybe at times I expect to have the value of 1, but because of the floating point precision errors, I get 1.00000000, and then some garbage that will trigger, in this case, the arccos function to give me not a number or undefined value. So here in this case, I know that I know that there are these limits that I can use, and so here I have a clamp node that has the low at -1 and the high at 1. And so if I pass this value here and I plug this in here, now you see that this is good. And so instead of having that error, I get both nodes giving me a valid value. So these are two ways to deal with floating point errors, either with comparison, or if you know there is a defined range of values, a critical range of values, you can always use the clamp. Cheers.